Hello everyone, this is Decrypt, and today I'm going to show you how a AES CBC bit or byte flipping attack works. So let me get you started with a little bit of theory behind the CBC AES encryption. So it's going back. Here it just says basically you have a plain text and you first XOR with that an initialization vector, which will give you another text that you then encrypt with an encryption key, finally giving out ciphertext. So this is again performed on the other blocks. So what do I mean by blocks is AES as an algorithm by default works on 16 byte blocks. So don't don't get don't get afraid about based on what I'm telling, right? So basically 16 byte blocks are basically nothing but 16 characters. Let's say you have some characters A to Z, and you know it's 26 characters, right? This will give you 26 characters. So what AES does is divide that into 16 characters and encrypt 16 characters at a time. So as you can see, what it will do is take the first 16 characters and out of this 26 characters and do the encryption, right? But what will happen to the remaining 10 characters? It cannot encrypt 10 characters because it's not how it is designed. So it needs at least 16 characters. So what it does is basically adds padding for 6 characters. So it adds 6 times pad to then get our 16 characters and then sends it to encryption. So this is our encryption 1, this is our encryption 2. So in this case we only have 2 blocks. So this is how it would look if we encrypt the alphabetical characters A to Z, right? So depending on how many characters you have, this will continue, right? Each character is a byte, right? So with that said, I think it's pretty straightforward, right? The first initialization vector is defined during the encryption, and the next step when you try to encrypt the second block, instead of using the initialization vector, you take the encrypted first block, which is ciphertext 1, which is ENC1 here, and then use that to XOR with the plain text of the second block, and then pass it down to the same key which was used before, and then give out this encrypted second block. So finally, it's going to print out encrypted block 1. Addition is not the right way to put it, but it's like appending the strings, right? It's going to append encrypted block 1 and encrypted block 2. So that's how it works. So let's look at the decryption process, right? It's actually the reverse of what we saw in the previous the diagram here. So instead of starting with the plain text, it's going to start with the ciphertext, and as you can remember, the ciphertext was given by block cipher encryption. So here, a block cipher decryption takes place using the key that was used initially for encryption. And as you can see, we are using the same key for encryption and decryption. So we are dealing with symmetric cryptography here. And then the final, once you decrypt that, and then you XOR with that the IV that was used for the first block and get the plain text, and take the ciphertext and again XOR with the decrypted second block to get the second block plain text and so on. So with that said, I'm going to show you a challenge that I came across on the web and show you and walk you through how to solve the challenge. So let's get started. So here's the code, right? So we have Python code basically using the Python packages crypto, and here we are getting 16 byte, which is 128-bit keys, right? We are using 128-bit keys, 128-bit initialization vectors, and it's just random bytes. And we have an encryption defined encryption function, and like I said before, we are defining the padding, and so we're going to pad it so that the block is 16 byte long, right? And then we're going to pass it on to the encryption routine. So actually we are first initializing our cipher variable with the AES object and providing it the key and the IV that we created in here, and then we are going to call the encrypt method on that object, and we're going to send the padded string which will return our encrypted string. And for decrypt we are doing the same, but here what we're doing is we're not doing anything with the padding again, because we are already going to get the padded encrypted string. So we're going to just decrypt it, but we're going to unhex it before we decrypt it. So unhexly 5 is oh my bad, it's like a function that you can use to convert characters into hex format, right? So that's pretty much it. So I'm going to make it run so let's go to the body before I run it. So it's actually creating, so in the main we have a socket server created, so it's listening on port 1337 on my local host. And what's going to go do is then call the serve forever function. So it's going to be just spawning off the the server. So the next thing is it has a task handler as the input here. So task handler is going to make sure it's calling the main here, right? So instead of the request, we're going to sending this s. So here we're going to print out username, provide username, password, all that, and we're going to print out the welcome message, which is this. And next thing is what we do is take the username and password that was given by the user and append it here and make it a message. So logged in username equals the username and the password. So if that matches this value, so we are having username and password here, then we're gonna say you cannot log in, right? If it doesn't match, then we're gonna go ahead and make a message out of that and encrypt that message and then send it back to the user. So the user has to type the encrypted another ciphertext, and this time we're gonna take that and use it as an encrypted message. So we're going to pass that encrypted message to a decryption data function, which is this. And upon decrypt, if it does have so decrypt data. So here in decrypt, if it has this value, then we're going to return 1. If not, 0. So 1 means true. So if check returns true, then you're going to say you logged in, right? But if you notice in decryption, the decrypt function here, we are looking for admin and password should be this. But in the very first step, we are going to make an assert statement saying only allow the user if the admin and password is not this. So basically, what we have to do here is give something else for username and password, and then figure out the encrypted format for this, and then send that encrypted text data as an input to this service. and which is going to let us in if the encrypt data decrypts to this value, right? So think about it, because we don't have the keys, right? Let's say this is running on a remote server and you don't really have the keys and IVs that is being used. So how can you decrypt the data without having the keys, and how can you hence log into the system? So let's try and launch that and see what happens initially. Okay, I'm running the code and connecting to it using netcat. So I'm typing decrypt, right? It's allowing me because it's not equal to decrypt 123. So I have to give some value here, and it's going to try and authenticate with that. So let's try with the actual value that we need to be having in the encrypted string to log in as admin, right? Yeah, so it's going to give us an error saying you can't log in. So what I'm going to do is, just so I'm past this function, I'm going to give this as a value. So I'm going to change the A to B, and I'm going to keep the value as it is. Right, so since we have changed the value, now we are able to get the encrypted form of this. So this is nothing but this message, right? So it's basically admin bdmin, and this is the password. This value here is an encrypted form of this text, right? So if you remember what I told before, this AES encrypts 16 byte, as a block. So if you look at the number of characters here, we can use Python to get the length. You can see it's 41. So 16 does not divide 41. So what will happen in the padding stage is this will become 48, because 16 divides 48 three times, right? By multiplying three times. So it's gonna have this encrypted value is essentially nothing but this 41 characters and followed by 7 characters that are used for padding. So I'm going to use what can I use? Let's use the dollar symbol for padding. That's not how it actually pads in real working scenario, but let's keep it this way as of now. So 1, 2, 3, 4, 5, 6, and 7. So we have 7 characters, which will make the entire string 48. So this, let's imagine this was encrypted into this, right? Also, if you remember the concept, going back, this encrypted first block is used for XORing with the decrypted second block to get the plain text. So what it means is this has 16 bytes and this has 16 bytes. So this is going to yield another 16 bytes because the block size is 16, and that 16 is then XORed with this 16, right? Imagine two boxes laying on top of each other, right? So let me draw it out. Yeah, let's do this. So for 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, right? So this, consider this as the encrypted first block, which is this, and consider the following as decrypted second block. Although it's decrypted, we still don't have the plaintext, because this encrypted first block has to be XORed with this decrypted second block to get the plaintext PPP, right? So in an ideal scenario, what's going to happen is it's going to take the first character or the first byte here, XOR with the first byte B, and then give P, right? That's the plaintext. So it's going to go take the second character or second byte, take the second byte of the decrypted second block and produce the plaintext of the plaintext byte, right, of the second block, and so on. So if that is the case, we can real quick check the length of the string that we got as encrypted value, right? So it's 96. So as you can recollect, what we did here in the code is in encryption function we return the hex format. So hex is basically these two characters form one hex byte. So if that is the case, this is 1, 2, 3, and so on. So we basically have to divide 96 divided by 2. We're going to get 48. So that's exactly what we sent, right? So we know that L got encrypted to E, right? And so on. Uh, Actually, L got encrypted to E4, right? And so on. So then what we need to do the next is find out how to change this B to an A, right? Because we need to send that here so that we are able to log in as admin. So if you want to change B, we need to change the previous block, which is this previous block to this is this, right? So let's count and see what we need to change on the first block to actually change the B to an A, right? So we know it's going to take 16 bytes or 16 characters. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16. So this is the first 16 characters, and this will be the first block, and it's the second block, 16 characters, is going to begin with B. So with that calculation in mind, we know that we need to be changing the L character to get the B characters, right? So just keep that in mind. So we know that L was encrypted to E4. So we need to find what B was encrypted to in this, the random byte. So just count 16, right? This is 1, this is 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, and this is the 17th character. So 17th character is B. So B was decrypted to 0, 1, right? I hope I counted that correctly, by the way. But yeah, let's go forward and see if I did calculate that. So L was encrypted to E4, B was encrypted to 0, 1. So we know that E4 XOR 0, 1 is going to give us the character B, and ASCII table will give us the value of hex value of B, right? Let's just use man ASCII and go and find B, which is 62. So it's going to give us 62. It might be very confusing at this point, but just hold on for a couple of more minutes and things will be pretty clear. So yeah, let's go ahead and make sure that I counted that correctly. Right, so let's take this and count the number of characters here. 32. Yes, so that's the first 16 bytes, right? So we know E4 XOR will get XORed with not 0 1, but it will get XORed with the decrypted 0 1, because if you see here, we are first decrypting the second block and then XORing with the first blocks to get the plain text, right? Okay, so this should be the case. All right, so we have E4 XORed with decrypted 0 1 to give 62. So we need to find the decrypted 0 1 here, because we know that E4 XOR with decrypted given by will give you 62, right? Then if we know that, it's basically XOR can be magically used to calculate other values, right? So let's say A XOR B gives C, then B can be calculated as A XOR C. So that's how it works. So applying the same formula here, we can calculate decrypted 0 1 as XOR of 64 and 62, E4 and 62, right? So let's just do that, and using Python, just copy that, and we need a hex of this value. So I'll tell you why we are doing all this, right, in a couple more minutes. So we know that this value 86 is the decrypted 0 1. So we know that now E4 XORed with 86, right, gave us 62. So what XORed with 86 is going to give us 61, because we need an A to log in as admin. Remember, we need to change the B as A. So 61 is the ASCII format for A, as you can see here. So that's pretty much what we're doing. So again, applying the same XOR formula we saw above, we can find out this value by XORing 86 and 61, right? So let's do that and change this to 86, and we have E7. So basically, we know that now E7 XORed with 86 is going to give us 61, which is the A, right? So what we need to do is basically change the E4 into E7, so that we're gonna, once it's get XORed with the block of the second block, which is the decrypted second block, which is the 86, it's going to give us an A, right? So let's try that. Just copy the entire encrypted value from here. Actually, just this. And we know we need to substitute E4 with E7. And here we go. We were able to successfully log in as admin. So that's what is called as byte or bit flipping attack. And we just flipped the first byte based on our calculation that we know that if AES is operating on a set of blocks and each block is 16 byte long, and we also know the plain text value here so that it was easier to find the actual length of the input, so we can calculate the, the number of bytes we need to jump over to find the byte that we want to change, right? In an ideal scenario, you might not know that. So not in an ideal, but in a real scenario, you would have to do or get this information, what is being passed as input, through other means like reading the source code, or try to fuzz the application and see what's happening. But that's basically what's how a AES CBC byte or bit flipping attack works. I hope you understood this really well, and please let me know if you really want to have me solve any other similar CBC bit flipping attacks that you have come across, and I'll be happy to do that. So with that said, I'm going to sign